afternoon, everyone. In this particular presentation, we are going to basically extend our lecture on delta function or the Dirac delta function, and we are going to learn basically how to use Dirac delta function to represent a point charge using the volume charge distribution. Now, for this, I ask you to suppose a point charge which is kept at a point r is equal to r naught. So, if we suppose a point charge which is kept at a point r is equal to r naught. And now I ask you, what is a volume charge distribution or what is a volume charge density of this point? So it is very obvious, since there is no charge kept except at point r is equal to r naught, so the volume charge density will be 0 everywhere except at this point r is equal to r naught, because there are no charges everywhere except at this point r is equal to r naught. So the volume charge density everywhere would be 0 except at this point r is equal to r naught. So the volume charge density everywhere except r is equal to r naught would be 0. Very obvious. And what would be the volume charge density at point r is equal to r naught? So volume charge density at r is equal to r naught would be infinity. Why? Obviously, the formula for volume charge density is charge per unit volume. Now, very obviously, the charge which is kept at point r is equal to r naught is q. But what is the volume of a point? Since the charge is kept only at a single point r is equal to r naught, so mathematically speaking, a point has 0 volume. So the volume charge density would obviously be infinity. Now, it is very obvious, in mathematics we say that volume of a single point is 0. So that's why the volume charge density at point r is equal to r naught would be infinity, and the volume charge density at all the places except at this r is equal to r naught would be 0, because there is no charge which is kept anywhere. Now I basically ask you to consider an integral. Now consider an integration of rho times d tau over the all volume. I will not write it again and again. It is very understood that I am referring to the integration over the entire volume. What is this? This is precisely the definition of a point charge. So you integrate whatever is the charge density, you take a very, very small volume d tau and you integrate the charge density over this small d tau and you integrate it over the entire volume. The answer would be the charge density. The answer would be equal to the charge q. Yeah. Now 1 over q integration of rho d tau, this would be 1. Okay. Now I ask you to consider this function only. So consider the function one over q integration rho d tau, this equal to 1. Okay, consider this function. Now if you think about this function carefully, the integration of this particular function is 1 if the point r is equal to r naught is included in this integral. Why? Because obviously if that point r is equal to r naught is included in this function, so this integral rho d tau would be q. Obviously, because that integration range contain that point r is equal to r naught. And as I just told you that this integration rho d tau is equal to the total charge. So yes, if you integrate this over the range, if point r is equal to r naught is included, so this integration of rho d tau would be q, and then this q divided by this q would be 1, right? So I would say that if the point r is equal to r naught is included in the range, in the integration range, then the integration of rho d tau would be q, and if you substitute this in this value in the above equation, you have q by q, which is equal to 1. So therefore, if the point r is equal to r naught is included in the integration, then this integral results in the value 1. Now what happens if the point r is equal to r naught is not included in this function? So obviously, if the point r is equal to r naught is not included in this function, then this integration of rho d tau would be 0, because there is no charge which is in the integration range. Since we have only a point charge at position vector r is equal to r naught, and that if that point r is equal to r naught is not included in the integration range, then this integral rho d tau would be 0, and then this function would be 0. So therefore, if the point r is equal to r naught is not included in the integration range, then integration of rho d tau would be 0. Therefore 1 over q integration of rho d tau would means basically this function would also be 0. Now if you look carefully, and one more thing, if you look at this function 1 by q rho, also 1 by q times rho of r, so we are basically talking about this function. Now this function is 0 everywhere except at r is equal to r naught. Yeah, because you see, everywhere except at r is equal to r naught there is no point charge kept, and if there is no point charge kept, basically there are no charges, so this rho of r is also 0. So this entire expression is 0 everywhere except at r is equal to r naught. And what is the value of this function at r is equal to r naught? At r is equal to r naught, 1 by q rho of r is infinity. Yeah, because at r is equal to r naught, what is the charge distribution? As we just discussed, you can see here the volume charge distribution at r is equal to r naught, or not volume charge distribution, the volume charge density at r is equal to r naught is infinity. So therefore, if you look at these, what I have just discussed above, aren't these the conditions for the Dirac delta function, for this function to be Dirac delta function, if you look at it carefully? So this function is 0 everywhere except at r is equal to r naught. At r is equal to r naught, this function is infinity. If you look at the definition of Dirac delta function, delta of r minus r naught is 0 everywhere except at point r is equal to r naught, but at r is equal to r naught, that function is infinity. So isn't this the definition of Dirac delta function? Also, that integral point, if the point r is equal to r naught is included in the integration range, then the integral value is 1. Remember that integration delta r minus r naught is 1 if that point r is equal to r naught is included, and if that point is not included, r is equal to r naught, then the integral is 0. So all this suggests to us, or all this indicate to us in only one direction. And what is that direction? That direction is that 1 over q rho of r, that is the function that we have considered, can be represented as a Dirac function in 3D. It's a very, very important result. And What is this rho of r then? Is obviously q times delta cube of r minus r naught. This is what we wanted to prove, that how to represent a point charge using the volume charge distribution. Okay, so if somebody asks you that how to represent a point charge using the volume charge distribution, so you would say that a point charge can be represented using the Dirac function. So in terms of Cartesian coordinate also you can write this. In terms of Cartesian coordinate you can write that rho of r will be nothing but q times delta of x minus x naught, y minus y naught, and z minus z naught. This is how you represent this in terms of the Cartesian coordinates. Okay. Oh, sorry. I should use delta here also and delta here also. Yeah. This is how you represent the charge distribution in terms of the delta function. Okay. So this is what I wanted to explain in this particular video. Thank you very much.